Daksha has been working with Virginia on the project we have with Southern California Edison. So we're going to hear about some stuff he's done with that today. He recently completed his master's in computer science here at CU Boulder. He worked on wildfire prediction with this project. And before grad school, he spent 2 years at Dish Networks as a back-end engineer on services supporting Sling TV. And he's now working as a Java developer at Motion Industries. So thanks, Daksha.
Hello, everyone.
Hey.
All right, take it off.
Yes. Thank you so much for the introduction. So yeah, right now I'm in Birmingham, Alabama. I just moved here like last week. So last month I graduated from CU Boulder, where I was pursuing masters in computer science. And until then, I was still working on this project. And once I graduated, I came to the city and now working as a Java developer. So this project had been you know we've been working on this project for about 1.5 years, along with Southern California Edison, who wanted to create a model for predicting wildfire, in for the next 3 months in Southern California. And I've been working on this project under Virginia since last year of January. So what motivated us to do this project, as we all know, due to the rising temperatures and the dry conditions and the increase in global warming, the fire seasons have become more intense and become more longer. And it's happening in the urban-based areas where people live, and it has uh, increased a risk for them as well as their properties. And the main motivator of these wildfires in these urban areas are human-caused wildfires. Um, and the and Majority of these human-caused wildfires happen due to the faulty power lines. The power lines which these faulty power lines cause sparks in the surrounding region, which get caught by the vegetation, and that causes wildfires. So uh, essentially our solution is to clear that vulnerable vegetation, the dry vegetation which surround these power lines, so that we can eliminate the fuel that causes these wildfires. So in a way, we want to interrupt the wildfire spread and help in preventing loss of properties and even lives. Since we were working for Southern California Edison, the study region which we decided to keep was the Southern California. Um, Now, before I move on to the next slides, I want to talk about the spectral signatures, which will be this will be useful in understanding our model and the entire workflow. So, what are spectral libraries? As you know that when a light hits an object, be it trees, humans, rocks, land, any of it, they reflect a certain unique wavelength, and this unique wavelength depends on the chemical and the physical composition of that object, right? So, for example, if you look on this diagram, we have the green wavelength, right? Since The green wavelength will absorb, I'm sorry, the green wavelength will, the green vegetation will absorb more, more green color and reflect less green color. That's why the value of reflectance over this green wavelength is lesser. Whereas the dry vegetation, the dry grasses will reflect more green color. That's why the value of reflectance over here is higher. Why this matters is because each object, since has a different wavelength, a unique wavelength, it helps us to identify different objects using these spectral signatures. And that's the basis of our entire model. We're using a model called MESMA to uniquely identify each uh, uh, uniquely decompose each pixel in an image to identify each unique pure pixel and the fraction of it. So this is our workflow. Our workflow is divided into three parts: the download, the preprocess, and the model. The downloading stage was downloading the Sentinel-2 images from the Sentinel repository. The next step is pre-processing these images, which is resampling the spectral bands, which have 20-meter resolution to 10 meters, and also removing the cloud cover. And the third and the final stage is the modeling part, where we used the Mesma algorithm to apply Mesma on these images and identify these pure pixels in the image. In the first step, which is downloading the Sentinel-2 images, we used Sentinel-2 repository for mainly three reasons. One, that it's public and free of use, and since it's available on the AWS bucket, we can easily integrate it using API calls from the AWS bucket to our database. The second, it offers 13 spectral bands from the visible spectrum to the shortwave infrared. This helps us in looking at different pure pixels and how we can easily separate them from each other. And lastly, it gives us as good as a 10-meter resolution, which helps the Mesmer model to accurately p- predict and distinguish these pure spectrals. The second step was pre-processing. The only step which this step involved was removing the cloud cover. This is an easy step because the Sentinel-2 repository also gives us the uh, cloud cover files along with the images, which tells us where these clouds are present for each pixel in the image. So essentially, we just took this cloud cover file and overlaid it on the images, and whichever pixels had these clouds, we made them as null values because we don't need them for the model. And the last step was applying the model on these pre-processed images. Uh, so on the hood, this Mesmer model, it would decompose every pixel in the image uh, to tell you how much fraction of each pure pixel is present in that image pixel. So how this works is that we built and extracted a database of all the pure pixels, like pure the green vegetation, the dry vegetation, soil, rocks, and created a database out of it in a spectral library. And with these pure pixels and the image, we the Mesma model found the best combination of the pure pixels in a particular image pixel with the best fit and least error, right? And and with this, we were able to see the proportion of each pure pixel in each image pixel. So, for example, over here, the green color here, the region, it tells us this is the green vegetation. The blue here represents the soil, and the red here represents the dry vegetation, which is our interest area. And all the other colors of different shades, like of blue and red, it means that it contains different combinations of these pure pixels. For example, this could mean this dark color blue could mean that it has some soil and dry vegetation in that particular pixel. Before I move on to the next steps, do any of you have any doubts?
I think you're good. I'm sure we'll have some at the end.
Okay, sure. Um, yes, so this was the entire workflow which we did for Southern California. The next step was MLOps. MLOps is nothing but to integrate these different stages, download, the pre-processing, and the model together. Before I move on, I'll just talk about the machine learning life cycle. The learning life cycle is, the complete life cycle of a machine learning project, which starts with a data collection. This means that if the project is about numbers, and we would, uh, financial data, then we would take some numbers. If it's about images, we might scrape some data of the internet. The second step is cleaning and preprocessing, where we clean these this data. Uh, in our in our case, the images, we cleaned it by removing the cloud. The third step is choosing a model, which is important because this will determine how well our project is working, right? So uh, this can depend on various factors. One, that we read previous research papers in that same space and see, which models worked the best for them, uh, right? And we can either choose like one model, or we could choose multiple different models and then compare them to see which worked the best for us. And the fourth step is training the model. So once we have chosen the model, we have cleaned the data, we would uh, pass that data through the model. That's the entire step. And evaluation and prediction is where we see what results we get from this model training. And the last step is deployment. So once we have built our model, we want to be able to use this model, right? So either we use it internally, or as a business, our user base will use it. So either we deploy it in the cloud or on premise. So that's the deployment part. And this is a cyclic process. So as we get more data, as we refine our model, this cycle just keeps going on. When I completed this project, all the stages were, on different notebooks. Like the download, the pre-processing, and the model were on different notebooks. And if Southern California Edison wanted to request for the image, a MESMA image for, let's say, last month, I would have to, uh, you know, run these notebooks individually, which would take a lot of manual training, as well as, this since I was doing it by hand, this would also mean that if there are any errors, I would have to go back and see what those errors are. At the same time, this would also increase the entire training time. So instead, what we thought is that, we would create a pipeline such that if I would have an input, let's say that the input is that I want to create the MESMA images for the month of May, right? And I would input that on the first stage, which is downloading, right? uh, this the first step would download the images on its own, and once the download is done, the second step would involve pre-processing it. This means that I don't have to intervene in the second step. It would just, once the downloading is done, the pre-processing step would begin on its own, and so on for the third step too. And the images would be then stored on its own automatically on some cloud. So this was the entire goal of using MLOps for the project. At the same time, um, let's say if I'm the only one working on this project, only I would know the steps of running these stages. To avoid that whole confusion and ramping up on the code, I thought it's best that, if there could be a pipeline that someone else could run it on their own without knowing what the code is doing on its own. So yes, with ML ops, we were able to, automate and streamline the entire ML life cycle, speed up the model deployment, support continuous training and testing. This means that I didn't have to, think about how to run the code, but my main focus was how I can define it better. And at the same time, it also reduced production issues and manual errors. The initial step of these three stages were the same. This means that every stage had its own Jupyter notebook and a Docker file, and all I did was that I built the Docker images with the dependencies for each stage, stored them on the EC2 instances, and deployed these Docker containers and ran them on the EC2 instance. Uh, and the workflow is such that so I created this MLOps pipeline on GitHub Actions because I just thought it's better to have the pipeline closer to the code itself. So uh, so all I did was that I inputted the parameters such as which month of the year I want the images for, right? It would call the EC2 instance, run the code for that input, save the images on the bucket, and just email me saying that your job is finished and you can take a look at the images. So to show you an instance of this MLOps pipeline, so as you can see, this is the GitHub website. I have my code here. The three stages are download, pre-processing, and the modeling. And this is the GitHub Actions where I have defined my three different uh, stages: download, pre-processing, and the modeling part. And I can, since I don't have the permissions to download to run these uh, stages, I can just show you an input, maybe output of. Oh, oh, okay. I was in silence. Sorry. Yes. So if I have to run the workflow, all I have to do is that I have to give the inputs, which is the start date, end date. This corresponds to which images I want for which month. And this is where the images will be stored. So once this runs, I'll have something like this. Um, yes, it's gonna look something like this, where the start, it shows me which stage it's on, right? It gives the input parameters which I gave on the GitHub Actions, and then correspondingly it also just shows me the status of how much downloading is done. And once it's done, it just says that download stage completed, and it has saved all the images on the bucket. And similarly, it also does the same thing for the second and the third step. Yeah. Yeah. That's all from my side. Thank you all.
Really neat, Daksha. Thank you. Do we have questions?
Using the GitHub Actions, do you not run into size limitations, or how does GitHub, do they charge you for that? How do you pay? How does that computation work?
Yeah, so GitHub Actions has free instances on which we run the pipelines. It does not charge us for running anything at all. And what do you mean by sizing issue?
Well, I just mean that's a lot of stuff to process. So, and they're pretty big files, right? So I just thought you could do
Oh,
it.
yes. So GitHub Actions doesn't process anything. All it does is it calls it SSH into the EC2 instance, and
Mhm.
EC2 instance does all the job.
I see. Yeah.
Yeah. And that's the same for all the three steps.
Cool.
So you have your AWS instance open on the back, like of your process.
Yes. Yes, it has to be open at all times when you want to run the pipeline.
Running, yeah, running and everything.
And so how long does that take to do like a 1 month block that you had for the area you showed us? How long does that processing take for a Mesma?
So each step takes its own time. The first step, downloading the images takes around 15 minutes, 20 minutes. The second step, the pre-processing takes around 4 to 5 hours, and the modeling, it takes around 1 to 2 days.
For one vaccine,
For 1 month?
1 month.
Questions? Awesome, Daksha, that was really cool. Thanks for showing us everything that you did here.
Yeah.
Yeah, thank you.
Thanks for sharing.
Thank you. Yeah,
Thank you so much.
good luck in your new position.
Yeah.
We miss you.
Come back.
I do want to come back, honestly.
Is it hot and humid in Alabama?
Sorry?
Is it hot and humid in Alabama?
Yes, it's always the same temperature. You never have to see the weather app, you know? It's always 20 degrees Celsius over here, day and night.
Has their hand up.
Yeah.
Yeah.
Looks like you have a question online.
Hi. Yes. Thank you. I appreciate that presentation. I have just maybe a couple questions about your workflow. So, is it correct that like all of your data that you're like downloading through the GitHub Actions is stored in your AWS account? Is that right?
Yes.
Okay. That makes sense. Yeah, I've been trying to like move a bunch of stuff over to Git management and having issues with large files, which Git doesn't love.
Yeah.
So I'm actually using Git LFS for that, which is also like not amazing. But can you tell us more about your like the Mesma algorithm? So like I guess I gather that like what you're getting for each pixel is like reflectance values for like different spectral bands. Is that correct? Your input data?
I'm sorry, I didn't get your question. The last part.
Oh, the input data to your Mesma algorithm. So for each pixel, you have, is it like reflectance values for like different spectral bands? Is that what's like being fed in?
Yes.
Okay.
So we have around 8 spectral bands, 8 individual bands which we received from the Sentinel-2 images. We overlaid them together as one image, as a TIFF file. And yes, we're using the reflectance values of these 8 bands together, along with the the database of the pure pixels as input to the model. Right, and this model, what it's doing is that it's using the root mean square error to find the best fit of the pure pixels in every pixel of the images.
I see. So, and what was there? Like, what were you using for your training data? Or am I also misunderstanding something there?
Yes, so this model did not need any training data at all.
Uh-huh.
Right, this was an algorithm which could just run with the spectral library and the image itself.
So I'm sorry, how do you verify if the classifications are what you want them to be?
Yes, so that's one thing we couldn't do, like, verify it using programmatically code. We had to do that manually. We have to see, well, we just look at the, the main image and the Mesma image and see whether it's able to classify rock as rock, soil as soil, and vegetation as vegetation.
Okay, so you're like kind of like visually ground truthing it
Yes.
against the imagery.
Yes.
Interesting. Okay. Yeah, just curious. Sorry, I also should have introduced myself. My name is Reed Humphrey. I'm a PhD student at the University of Washington.
Oh,
Um,
hi.
yeah. Anyway, thank you. Cool presentation. I appreciate it.
Thank you.
Any other online questions? We didn't miss any more, did we? Okay. Well, thanks, Daksha. Appreciate it.
Thank you so much. It was nice meeting you all.